Well, now we're going to look at some methods of solving systems of homogeneous linear equations. And this is going to require some linear algebra. So this is stuff you will have seen in the class linear algebra if you took it, or you will see it in linear algebra class when you take it. But you've probably heard of eigenvectors and eigenvalues, and we're going to need to use those. We're going to have to be able to compute them from a coefficient matrix. And I'll do a little example, at least getting partway through it, and maybe that'll remind you what eigenvalues and eigenvectors are. Let's start with an easy example. Before I go over the theorem, let's just try to remember what eigenvalues and eigenvectors are. If we have a coefficient matrix A, it'll be a square matrix. It could be a 2 by 2 or 3 by 3. 3 by 3 is probably the biggest matrix we'll deal with. If you have A times this vector, AX equals lambda x. That's the same x vector on both sides. So we have a square matrix times a column vector equals lambda is just a real number. And that's the same vector on both sides. So what does that mean? In this case, basically, this coefficient matrix is like a transformation. It's like a function. It's doing something to this vector. And in this case, all it's doing, it's equivalent to multiplying this matrix times the vector, is the same thing as multiplying it by this constant. Well, when you multiply a vector by a constant, all you're doing is stretching it if the constant is bigger than 1. Shrinking it if it's between 0 and 1, and if it's a negative number, you would be it'd be going the opposite direction, but it stays on the same line. So applying this matrix to that vector simply stretches it or shrinks it, basically. Could be in the negative direction. So if this is true, and I need to say for x not being the 0 vector, the column 0, if that's true, then lambda is an eigenvector of A, eigenvalue of A. So, we're going to have to find that eigenvalue. Let's say we have, let's say A is 1, 2, 4, 3. Let's find the eigenvalues. We'll find both eigenvalues, and I might find eigenvectors associated with one of them and leave the other one for you to do, because I'll probably run out of room here. Let's say A is equal to that. Well, write this down. The eigenvalues of A are the solutions to this. That equation. DET is the determinant. So we have the inside, we're taking the determinant of what matrix? A minus lambda I. I is the identity matrix of the same size as the matrix A. So if A were 3 by 3, we do have 3 by 3 minus another 3 by 3. And when you multiply the lambda times the identity matrix, which is all zeros except ones down the diagonal, multiplying that by lambda gives you all zeros with lambdas down the diagonal. So this is called the characteristic equation. The left side would be called the characteristic polynomial, slightly different than the one we've seen when solving individual homogeneous differential equations. So the eigenvalues of A are the solutions to the characteristic equation. So let's figure out, let's do that. Let's solve that to find the eigenvalues. All right. First, note that A minus lambda I, I'm running out of room, I start writing smaller, is equal to what? Well, that's 1, 2, 4, 3, that's A, minus lambda times the identity is just lambdas down the diagonal and zeros elsewhere. So that would give us a 1 minus lambda. The 2 and the 4 stay the same because we're just subtracting the corresponding zeros. And that would be a 3 minus lambda. That's the matrix. Okay, now that we know that matrix, the characteristic equation is going to be, this tells us 1 minus lambda, 2, 3, oops, there's a 4 there. Take the determinant, the vertical bars are just the determinant, equal to 0. Well, that tells us that, how do you get the determinant of a 2 by 2? You take the product, this product, minus this product. So we get 1 minus lambda times 3 minus lambda minus 2 times 4 is 8 equals 0. Okay? And that gives us, if we FOIL it out, we're going to get a 3 minus lambda minus 3 lambda. Lambda is minus 4 lambda plus lambda squared minus 8 equals 0. Let me rewrite that. Lambda squared minus 4 lambda. 3 and negative 8 gives us negative 5. And now let's factor. Lambda, minus 5 and positive 1. So setting each one of those to 0 gives us that lambda equals 5 or lambda equals negative 1. So we found the two eigenvalues. Now, those are the two eigenvalues associated with this matrix A. Now let's try to find the eigenvectors associated with one of them. I'll just pick this one. I'll let you find the eigenvectors associated with this one. Well, there are going to be an infinite number of eigenvectors that will work. We'll find out. They'll be easy to characterize, but an infinite number of eigenvectors corresponding to that lambda. Remember this? We need AX equals lambda x. All right, well, lambda is a 5. So that gives us actually let me go downward here. A is 1, 2, 4, 3. X equals 5x. Okay, let's go this direction. I'm going to put everything on the left-hand side. And actually, I think I'm going to go back to writing this A. Okay, so I subtracted 5x from both sides. Now remember what we're getting here. When you multiply A by this column vector, you get a column, and negative 5 times a column is another column. And so this is a column of zeros. And then I get A minus 5. I'm going to have to make one little mod here. You can't take a matrix and subtract the number 5. A might be a 3 by 3 matrix or a 2 by 2 matrix, but if we do this, it works out beautifully. Now 5 times the identity is a matrix, a square matrix, the same size as A is. So this will be the matrix with all zeros and 5 down the diagonals. Down the diagonal. Okay, so we get now, I'm going to go over to what A is. 1, 2, 4, 3 minus. Well, 5i is just that. And actually, maybe I'll start. The vector x is, we need two variables. I probably shouldn't use x again, but I will. That is the vector x. It's got two values because we're dealing with 2 by 2 matrices, and the 0 vector looks like that. So this gives us 1 minus 5 is -4, 2 minus 0 is a 2, 4 minus 0 is a 4, 3 minus 5 is a -2. Now we're doing simple linear algebra. We could use the Gaussian elimination method, matrix method, where we say -4, 2, 4, -2, and we get the augmented matrix. This 0, 0 came from here, and we'll solve this to figure out what little x and little y are. And if you remember, this is like the little x column, that's the little y column. So before I do anything, I'm going to add equation row 1 to row 2 to zero this out right here, to zero out the 4. We're just using elimination now. So if I add row 1 to row 2, I'm going to get -4, 2, 0, 0 if I add, and then 0 if I add, and 0. And by the way, it's perfectly normal to get a row of zeros here. If I had two what are called linearly independent rows, I would get exactly one solution, one eigenvector. We're always going to get an infinite number of eigenvectors. So all we need to do is solve that top equation. Since the bottom one is all zeros, that means that -4 times x plus 2 times y equals 0. There are going to be an infinite number of solutions, so maybe we'll solve for y. You wouldn't have to, it doesn't matter, but 2y equals 4x. Right? I added 4x, so y is equal to, dividing by 2, 2x. So our entire set of solutions, we're looking for this, right? X bar is, let's just make x there and 2x there. Now remember, this x vector is just a representation for this whole vector. It has nothing to do with this little x here. I maybe should have used different letters. So this is the infinite number of solutions. So let's pick one. How about if we pick, say, if x equals 1, then we would get 1, 2. That is an eigenvector, one eigenvector, associated with lambda equals 5. So lambda equal 5, x bar equal to 1, 2 is an eigenvalue. I abbreviated that E value. Eigenvector pair. And it would have been fine if I picked -1, -2, or 2, 4, or anything other than 0, 0. It needs to be a non-zero vector. Okay, hopefully some of that rings a bell about computing the eigenvalue, and we computed both eigenvalues of this 2 by 2 matrix, and then we computed the eigenvector associated with one of them. I don't have room to do the other one, but trust me, we'll be doing a lot of this in the upcoming videos.